Hello, everyone. Welcome to this version of this webinar of our SPE Permian Basin Chapter Data Analytics Study Group. We're excited to have Erica Conan here with us from Reveal Energy Services, finding new ways to look at your old data. Just to kind of do a little preliminary stuff to let you know what's going on. She will do a presentation for about 45 minutes or so, and then we'll have Q&A at the end. You have two options on the Q&A. You can either raise your hand right next to your name. There's going to be a little button to raise your hand, and you can ask your questions verbally at the end. Or if you like to, there's a question panel. You can type your questions in, and I will ask them to her on your behalf. Again, I will be emceeing the Q&A at the end. So if you have any other questions or concerns, feel free to ask during that time. And Erica, would you like to take it away?
Thank you for the kind introduction. Yes, so this presentation was 1 week delayed because I think 2 weeks ago we were still fighting with cold weather here in Texas, but it has warmed up quite a bit, so I think we're ready to go for this one. So the title of my talk is Finding New Ways to Look at Your Old Data, and hopefully along the way we'll find some new ways of looking at data that you have recorded from unconventional wells. So this is the statistics that one of my colleagues kind of put together to kind of realize how much data we're actually collecting over the lifespan of an unconventional well. It starts with your geology and drilling and completion and other diagnostics, microseismic tracer, all the good stuff, and eventually production. So there is constantly, these wells are being monitored and measured, and data is being gathered in all kinds of ways. And the whole, besides regulatory reasons, the whole reason why we are collecting this data is that we believe that data leads to understanding, and this leads to action that eventually creates more value for our shareholders. But there is kind of a challenge here. This bridge from data to understanding, it's one error in this picture, but actually it involves a lot of work, as we data scientists know. This is not a trivial task. It's not a linear task, and we kind of need to build tools and work ways to make this transition from data to understanding nice and smooth, repeatable, insightful, and so forth. So let's. So we were facing the same thing at Reveal. So I'm going to take you a little bit through a timeline of how we came about building this bridge from data to understanding. So the software that we are currently using, it's an internal software that we developed, is called Orchid, and it's really an integration platform for all kinds of unconventional data that was collected on your well. And initially, this was really built as an internal tool to kind of speed up of data loading and cleaning, and it really helped a great deal. But then early last year, the market started to shift, and we really saw this need that actually bringing this tool to the market could really help operators, could really help data scientists with operators to excel building their workflows, and to help with kind of the data dilemma that everybody's having, like, how do I handle all of this? So in order to build something that could be used externally, what we decided is to kind of kick off in July 2020 with a beta program with 30 operators and consultants that were participating. And this beta program really helped, to put kind of a workflow together, a concept together that was very flexible, that and could really be used by engineers and data scientists all together. So it came to the market end of last year, beginning of this year, but what I'm going to show you will be really build on all of those learnings from 2020. So a lot of people participated. So the workflow that we put together has 4 basic steps. The first step is all about efficient data loading. bringing data sources together that you may have in data warehouses, that may be in all kind of databases, or that may be on flat files on your file servers in CSV files and Excel files and all of that. The second step is really QC'ing that. Not all data is recorded perfectly, and most of the time it's not data ready, as we say. Analysis ready, as we say. Most of the time it needs some kind of cleaning. It needs some kind of step to actually improve the data quality and consistency. After that, it's data fusion time, and that is really where you're starting connecting the dots within those different data sets and really start finding value in the intersection of certain data sets. And I know it sounds very abstract, but throughout the presentation, hopefully it will become much more clear. And then the last step is really value realization, or the discovery phase, value discovery. And that is where really you start having like, oh, this is a good idea. Let's bring this to my manager, or let's discuss this with my team, because that is where you have kind of create you got a new insight, a new idea that you think is of value to your company. So we did a little bit of like a background check, and there was kind of the 80-20 coming out. Initially, also internally when we started out, like 80% of the time, it's very sad, we spent with data loading and QC, and about 20% of the time we actually spent in what I would call meaningful analysis, things that really start moving the needle. And we wanted to shift that, right? We really want 80% of the time spent on meaningful analysis, and 20% of the time on data loading and QC. And also, you don't want to do that repetitively. Once you have kind of high graded a data set, you want to capture, you know, what you have done, and then move on and never have to do that again. So that's kind of where we are. So if we would look like first, like how we would tackle data loading. So I want to give you a very quick demo of how data loading is being done within ORCID. And what I will do is I will start a new project, for example, a test project, and we can define what kind of units we want to have. We can define what time zone we want to be in, and we can define actually in what kind of reference system we want to build this in. So what we can do is, once we have done that, we can start our data loading process. And like I said, what we want to build is something that is, you know, very easy to use, and something that that is not tied to a single vendor or a single customer. So the first thing, if you want to build a project, is you need some kind of project geometry. You need to have locations of wells, you need to have location of geology. So the first thing in this case, when we would like to, you know, to bring in some well data, is defining where those wells are actually located. And this is all of these databases you can load in the data loader, and you can see they're nicely organized, and it works very much like Excel. You have with the wizard of loading. So I will run through it really quick. So we'll have well names, we'll have easting positions, we'll have northing positions, we'll have Kelly bushings, and we'll have ground level right there. So we can preview, and there we have our wellhead locations somewhere on the planet. And very much so, we can also do the same thing. For example, when we want to load well trajectories, we'll just select the drilling survey. In this case, it's you do it load CSVs and Excels, very straightforward. Just get one in, and then I'll stop demoing. I just want to give you a feel of you know, how we can load data in here. There we go, and we have some azimuths. We can preview it. So there is your well trajectory of your first well, either in a plat view or maybe in a cross-section view. So that's that for the data loading. And you can do that for all of your wells. You could see data loading is very straightforward for all of those kind of diagnostics, especially, for example, microseismic and tracer, which can sometimes be challenging to load. That's easily done. So here are all the little pieces of data that we typically would be able to load in there. And for you as data scientists, I think how the data is then eventually stored is very important. So what we came up with is a very standardized but open data structure. So everything, if you save a project, is stored in what we call an ifrag file, but you can unzip that file, and in that file it has a folder structure, and on top you have a JSON file that organizes that folder structure. So within there you have, for example, here the different well metadata information, like the Kelly bushings and the ground level as I just entered them. So you can always reconstruct by going back to the JSON file. You have all the data that you would load, for example, your well trajectories, your stage locations, your treatment data. You have them nicely organized in folders, and it's standardized all the way really to the individual CSV files for each completion. One thing that I wanted to say is that we did not kind of develop this independently. We really want to make sure it's open so that everybody can use it and not have to redo any work of this. But also we want to align with broader industry standards. So there is basically probably many of you have heard about this. It's called the Open Subsurface the Open Subsurface Data Universe. It's really a collaboration of really, if you go to their website, of hundreds of operators, service companies, but also more tech companies like Amazon and IBM and all of those working together to find broader standards that really this industry needs. And they're working on a lot of pieces to build these REST APIs, but really the data classification for unconventional wells, that is where we try to mostly align, and we're actively contributing such that what we develop is really in relation also to what's relevant to the industry. So hopefully I did not spend too much time on that, because where I wanted to go is really to the data QC part. And I've looked at a lot of unconventional data in the past. I would say 6 years I was very heavily involved, and I kind of made the top 3 of data quality issues that for me come across. What we find a lot is in the completion summaries, there is a lot of inconsistencies in the data that is being stored. For example, if you look at post-job reports, start and stop times for completions, ISIPs, pump volumes, breakthrough pressures, many of those they are often manually entered and not always very accurate and consistently done. So when you start comparing these numbers from well to well or stage to stage, inconsistencies may arise that may help you lead to wrong conclusions. So that's kind of the first thing that that could be a problem. Another thing, if it comes to data, I kind of try to use the most nice words for what I can say about data formats. It's bespoke, but honestly, it's very chaotic. There's a lot of vendor-specific formats that are being used. There is kind of what I call header randomness. There is, if you look at different CSV files and Excel spreadsheets, there might be like very much arbitrary use of headers. Different use of units. For example, if you think about volumes, that's cubic meters, but also gallons and barrels and cubic feet and so forth. So there's a lot of unit conversion happening in this industry, and with all those conversions, little mistakes might be made. And just simple out data gaps. There are, if you look, for example, at large time series data, you will find that sometimes like large sections of that data might be missing because gauges might be not switched on, or batteries died, or you run out of memory. So a lot of things might happen there. But I think that the top one, and this is because I've looked a lot of pressure data, so actually my top 3 might be a little bit biased by that. are timestamp issues. There is, if you get time series data from different data sources, so for example, your CSV files with your treatment data, your pressure data, even microseismic data, they very heavily rely on, or offset strain data, another very good example. They very heavily rely on making sure that everything is synchronized in time when you want to compare action and reaction from one well to the other. And when you have different vendors, they all have their clocks set slightly different. So time synchronization issues are very, very present in this industry. Time zones. It's a big country here, so we have to work across different time zones, and so you will see sometimes these hour differences. Same with daylight saving, always a big thing when you have projects running through March or running in the autumn. Be careful of that. And crop formats. Sometimes, for example, if you open a time series data in Excel thinks that maybe you're not so much interested in the seconds that were also included in the data structure. If you then resave your Excel spreadsheet, actually you've just lost that second information data. So those are the majority of the data issues that we found, and some of these actually can be solved. Some of those, of course, not. When data doesn't exist, you can't patch it, or you have to use very special machine learning things. You might be able to patch some of that data, but most often not. Or some other things can easily be corrected. So what I wanted to give you is a little bit of a preview. And I'm going to unload the project that I just started to go to the project that I really want you to show. Let me see if this is the right one. Yeah, we're in the Birmingham. So when we think about time synchronization problems, one that is very common is, for example, like I said, completion data not being aligned with offset pressure data, or strain data or microseismic data not being aligned. So what I wanted to show is one way of analyzing if your stage times actually are aligned correctly. So what I've already loaded in this project is the CSV data, so the treating pressure, pump rate, and proppant concentration for all of the stages on this path. And I'm not sure if they're all in the exact right place. So for this project, we were lucky that we actually had a reference pressure also in this project. So now we can double check whether or not the individual CSV file here in this black line actually is overlaying with this long-term pressure that was recorded, which has the timestamp that we would like to sync to. So when there is a data mismatch, you can actually drag and drop or auto calculate where your CSV file should be, and the correction time would be applied to the individual CSV time. And you can do this, of course, for all of the stages. And this gives you a good way to make sure that all of your stages are QC'd. You can. I already did this process, so I'm kind of repeating. That's why everything's so perfectly timestamped. But you can see for the individual stages, it's not big that you're off, but typically you're a few seconds off, like 20 seconds before or after. And if you do like really accurate time synchronization, that might be a problem. So this is one way to overcome that. Another thing that you want to, for example, QC for is really like the start and stop times of a stage. And it might be different depending on what you're looking for. So this is again the treatment data that was loaded for an individual stage. We have this for all the stages. I can just mark through them. And depending on whether you want to define the start of your stage, for example, at where you start the pump, this would be your start. If you want to define, for example, a little later, then depending on rate, then or breakthrough pressure, you might want to define that start time somewhere else. But you can easily here adjust it and confirm it, and you can see that it's being updated there. So this is a very quick way of individually QCing and then storing what you have improved on your data. The last thing, I'm just going to skip one, and it's really, for example, looking if your ISIPs are picked correctly. So a lot of that data is directly taken from the post-job reports, but many of our customers and also data scientists, they kind of want to take their own view and want to see if the ISIPs are being calculated correctly. And here you can easily QC all the individual ISIPs. So the gray one is the one that was loaded, taken from the post-job report, and then the red one is the corrected one after review. And you can see there are slight differences between them because everybody kind of picks them differently. So this is hopefully kind of a flavor of QC. There are many other things that you can QC. For example, actually we did one and I kind of didn't show it. When I showed you where these well trajectories actually are on the planet, the fact that you could see that these wellhead locations landed exactly on your path so you could easily see this in this a satellite image. That's another good way of QCing, making sure that you at least have your wells in the right spatial location. So now we go to the more interesting part where we want to spend 80% of our time, and that's the fusion part. And it's kind of a term that we use because it's kind of a stage which is not so well defined. Of course, for data loading and QC, it's very well defined what your objectives are. For fusion, it's much more free form because this is really where you want to build a workflow, and we don't want to limit you to a single workflow. We want you as data scientists to think about what would be a meaningful workflow to do. But I will give you a few things, that could be very helpful, just to give you an idea. One thing that we try to do for our customers as much as we can is co-visualization of different data sources. So here I just took a snapshot of, for example, this is a well that was completed, and this was another well as a parent well, and this was another parent well, and these blue markers, they indicate tracer recovery. So you can see like for which stages the most tracer was recovered. And then these little histograms, they represent cross-well communication, pressure communication during completion. So with these two data sources kind of combined, you can see like, hey, for which stages did we actually have a lot of tracer communications, and for which wells, for which stages did we have a lot of pressure communications due to completions. And by just looking at that, you might find that actually they trend very well together, or you may find that they actually are not trending together. And then you can start thinking like, so why does tracer show up and not pressure, or the other way around? Another thing that I think is always very important is to co-analyze different time series. So we have some tools built in that really help you like look at different time series in a synchronized way and apply meaningful filters to those time series, such that you can learn from that. And then the last one are what we have in there are what we call discovery grids. They're basically, it's kind of like a built-in Excel with all the flexibility of the pivot tables and all of that. So it can give you a good way to analyze different kind of numerical data that you have entered. So what I wanted to do is give another short demo, and there is a lot of talk in the industry, for example, of volume to first response. And what volume to first response is, it's a way to try to classify parent-child interactions, pressure interactions during well completion. So if you're pumping fluid into a single stage, you will, during completion on the parent well, you may see a pressure response. And depending how much volume you have pumped, so sometimes that pressure response, you will see that very early on in your stage, maybe after a few hundred barrels, or for some other stages, that pressure response may become much later. And you so volume to first response really tries to to pin down that specific value for each of those individual stages. And what we hear from customers is that this can be kind of a tedious task. So what you try to do is accelerate that a little bit. So what I would like to do for that, I would like to use what we call the multi-track editor, and that's where you can analyze time series in a synchronized way. So we have parent well data, we have downhole pressure. So let me bring that in first. And what we also have is the child well pressure. So basically that's the treatment data right here. So let me bring that in second. So here you can see the individual time series that was recorded on different wells, but everything's time synced. So so that's nice to look at. Let me zoom in a little bit in the time so you can kind of crop the time. Let me crop it a little bit. There we go. I'm going to bring in a few other time series. Here's another one. And here's another one. So as we are looking at this, we can see that that as you're completing certain stages, we actually are seeing pressure responses on the offset well, and you want to investigate maybe per stage per well what pressure response is creating the most offset pressures. But one way to look at that is to look at first or second derivatives. So if you try to analyze a time series, applying filters to those time series is a very important thing, and everything's built in kind of natively. So you can kind of, for example, resample if your timestamps are too big, if timestamps are too small. You can add a first or second derivatives. So let's add a second derivative very easily, and you can see how this changes your time series. So now if I want to kind of pick moments of where I actually see pressure interference, I can say like, hey, let me bring up, when are these accelerations in pressure responses exceeding a certain value? So I can look, for example, where those pressure responses are maybe greater than a let's say a certain value, 0.05. And this immediately gives me some intervals in time for which we see these pressure responses and when they're happening. You can also look like, hey, when are certain wells being completed? So you can see that this pressure response is actually very much in line when you're completing well C3. So you can look at this in greater detail, and thereby creating volumes to first response, because this gives you the timestamps to investigate when you're completing these wells. So this is a very nice way to kind of co-analyze different time series. So what I've showed you was a lot of graphical interface and a lot of buttons, but I know that all of you actually might be familiar with more scripted coding languages. So currently ORCID supports externally the Python API. So it's public. If you would go to this pypy.org website, you can actually find our ORCID API there. And what it has is all that functionality that I just showed you in the graphical user interface. It has all of those same concepts also built in as these Python API packages. And so I'm just bringing up a Python notebook. So first, of course, you have to pip install the Python package that I just pointed you to. But from that point onwards, you can start loading different, or first you have to import your ORCID and import some packages. And then what it can do is it can actually load your Python, so your ORCID project. And like I mentioned, everything or project are stored as a .ifrag file. So here I just say, hey, ORCID .load project, and I just point to that file. In this case, it's on my local file, but it might also be on a server. So as you do this, as you run this, and it takes a little bit of time, so I don't want to do it here. It loads your project that we were just looking at. So it has all now that data natively now in available for your Python analysis. And there are a lot of support functions in the ORCID API, but if you want, you can also define your own functions. And I think that's a lot of what our data scientist customers do, because they want to experiment with different kind of definitions and different kind of way of looking at it. So here just implemented some peak finders and how do you define the time to first response. So here, this is where it becomes interesting. You can kind of take the pressure data, the time series data that you saw in the multi-track editor that I just dragged in. You can also just get that data. You can pull it straight out of your project objectives and get a certain time series data. And in this case, we wanted to have the time series data for the parent well P1, and especially the downhole data. So it pulls over that data. And so forth. So then you can start looping over wells. You can calculate, for example, pump volumes. You just integrate your rate from a certain stop to a start to a certain stop time. You can do the same thing for calculating proppant, either per stage or for a certain time slot within that stage. You can calculate distances between the wells, between stages, because you have that whole ORCID data structure available within Python. So, and of course, you can pull in all your plotting packages as you please. Probably you're much more familiar with the more fancier plot options, but here are just some straight XY scatter plots. You can have multiple projects loaded, of course, so you can start comparing different projects, as you can see here. So this is kind of, the way that we kind of opened up the software for further analysis, a further development for everybody, really to build their own workflows and to find new ways to look at data. So I really encourage you, if you have the chance, to kind of explore this. And then the last one, so once you have built all of those workflows and you're happy with those, you can share those with your colleagues, and you can test them on different projects and kind of build up the knowledge across different assets and different teams. And so the value realization is really where you have executed these workflows and you've really come to learn certain things. So this is actually the most important point of all of the work that we're doing, but it's also hard to capture, like, what is it exactly? But what I can tell you is that, for example, customers, they have looked at volume to first response between parent and child wells and identified if they're, for example, overcapitalizing their wells or understimulating. So that is, that has a big impact on driving costs. For example, they also looked at field efficiencies, for example, non-productive time, because you have all of those start and stop times accurately in the system. You can easily see if there are certain things that kind of slow down switching between wells, switching between stages, and if there are some efficiency gains there. We have seen customers that looked for certain, like, what's the amount of horsepower does it take to complete a certain stage in different completion design and different horizons. So not every rock treats equally or needs the same amount of horsepower to pump down a certain amount of proppant and slurry. So we have seen a lot of that. But actually, I think it's kind of limitless, especially when you start bringing in other diagnostics, for example, tracer data and microseismic data. We are starting to bring in offset strain data, so you can really start building these analysis in there. And especially, like I haven't showed you, but I think the co-visualization in 3D space, it's a very good way to collaborate and hopefully learn a lot about your wells. For example, you can bring in your observations that you have between the wells, and you can bring in the microseismic. I don't know if this project has microseismic. Yes, it has. Or it can bring in your tracer data and so forth, and you can show all of that and start, moving that in time, in space, to learn more on these wells. Oops. So, like I said, this is really the value discovery. Is really the collaboration. We have a kind of a community platform where it's kind of like a structure where you can post certain questions and when you can share certain ideas. So that's right there. So I want to really thank our development team who has worked throughout 2020, mostly remotely, to develop this platform. And we mostly share everything through Teams. So this is the theater view, or the all-together view of some of our developers. I took it this morning, and we had a few people who got 3 people that could not attend. But these are the people that make it happen. And I really encourage all of you to kind of look at your old data and hopefully find some new ways to find very good and meaningful workflows in there. So with that, I've come to the end of my presentation, and I'm looking forward if you all have questions.
All right, thank you, Erica. Thank you for that great presentation. It was very informative, and I can't wait to have some conversations with you about this stuff in the future. Definitely think I could find it useful at our company as well. So again, to kind of echo what I had said both in the chat and at the beginning, now we'll do the Q&A. You have a couple options for Q&A. You can either raise your hand, which is going to be the little icon that you can press to raise your hand. You can ask your question verbally, or you can just type your question into the question panel and I will ask the question on your behalf. It looks like we have a couple of questions already in the panel, so I'll go ahead and start off with those. And feel free again to just either submit those or whatever you'd like during this time. So we'll go with the first one from Ali. It says, what are some of the ways this tool can enable cross-disciplinary conversations on our asset teams?
Oh, very good question. I think it starts, I'm trying to bring in this picture. So it brings in a lot of different data sources. So it brings in your drilling data. It might have logs. It brings in microseismic data and other geo data. It brings in completion data. By having all of those different data sources from those disciplines in a single platform already should kind of foster collaboration. But also the data formats are kind of easy to move back and forward between the different teams. And I think once you have all of that together, we should stop building PowerPoints and just really, share the 3D visualizations and time displays, and have teams kind of collaborate in that kind of way and really discuss like, okay, this is what we see in our geology. Okay, this is what we see in our treatments responses in the field, and then start sharing our ideas of like, how those things really impact each other.
I have to remember to unmute myself. Okay, great. How are these conclusions best presented from the data analyst to the engineering teams and management?
That's a good question. So we have 2 kind of ways that you can use this platform. One, it's the full mode. So you're the analyst and you load all the data and you work with it. And then what we have is another option, and that's the community license. And think about it with what you have with Adobe Reader. You have like the Adobe Pro, where you can build your PDFs and do everything with it. And then you just have the Adobe Reader, which is a very affordable option for everybody to use. You can load in the IFRACs that your colleagues have IFRAC files that your colleagues have created, and everybody can look at it at their own computers and at their own time, or in the meeting rooms and discuss. But by having this two-tier structure, we hope that that we can create these interactive data sets and not be stuck with static PowerPoints.
Okay, I like that. That's a good analogy. I like that one. So I have one question for myself. How has, I know it seems like you have been working with other companies already, maybe other operators and such, and it seems like you've maybe done some more developing on that. What are some of the major changes or developments that have occurred with this tool because of the interactions you've had with some operators and such?
Oh, yes. For example, yeah, many things. Definitely at Reveal, we cannot claim like full responsibility for all the ideas that are captured in here. But for example, the displays of the tracers, like really showing them in 3D, showing them interactively, that was really in collaboration with people from outside of Reveal that came up with these ideas of how to do that. Also, the need for analyzing volume to first response really came up from a beta user question. Calculating breakthroughs or pressures, or picking up moments of ball seats in these slide and sleeve completions. I haven't shown it, but those were all kind of questions that were raised by customers, and then we go back to the drawing board and think, okay, how do we realize it within this platform? What development is needed to make that happen? And we have done a lot in the past year, but we are continuing exactly on that same route throughout this time period.
Okay, cool. Another one, let's see, what are customers doing in the volume to first response, doing with the volume to first response once that it is calculated?
Yeah, it's a very good way to kind of capture data from how child well and parent wells are interacting during completion. And by doing this in a very systematic way, you can do that. Normally this analysis would take a lot of time. Now you can do it in a few minutes once your data is loaded. So that makes it possible to do that over a large number of wells, and you can build up your statistics. Like, hey, this well has been online for so long. These are the types of volume to first responses that we're getting. This is the magnitude. This is how much volume we pump. You can look at go back to horizontal spacing of the wells, or vertical spacing to the wells, the types of reservoirs. So really building up those large scale statistics, I think that's what people are looking for. Also, they're looking, for example, if those volume to first responses can be changed by maybe repressurizing parent wells, or you can't really repressurize, but at least topping them up. Yeah, so that's really kind of what we are currently seeing, that these volume to first responses are being used for as a first measure to kind of gauge parent-child well interactions.
Okay, cool. Okay, let's see. Got any other questions or anything else? Wait a couple of minutes and see. While we're waiting, I will let everyone know that there will be, this is being recorded, and there will be a way to go ahead and get to the recording. We'll send out emails to those that have attended, and also to the presenter. If they'd like to share the recording itself, you can do that as well. So just a little bit of housekeeping on that as well. Okay, let's see, one other question. I have another question. So I know, like something like this, a platform like this, like you're saying, working with operators and such like that, it's always evolving. There's always new ideas coming up. without maybe showing your hand too much, because I know sometimes you don't like to show your hand too much on things that you're developing. Is there anything upcoming with this, or anything that's exciting that you're looking to add to your platform? You feel like you're pretty excited about?
Yeah, so this so it's in the pipeline, so I can easily talk about it. Really, this quarter we have been very heavily working on adding geological data, what you've seen is a lot of completion data and diagnostics data, but having formation tops, having drilling logs, for example, mechanical properties along your well bores being displayed, such that you can see, like, hey, where I'm completing these stages, we're in this kind of rock, or this is the gamma profile that we got back, and these stages are in this gamma profile. So those things are coming really at the end of this month. So and that's another. So now we're very heavily on the completions, but with this addition, having more abilities to load geological data in here are really right at the horizon.
Awesome. Sounds great. Sounds exciting. Okay, well, I guess we'll go ahead and wrap that up. Once again, thank you very much, Erica, for joining us today and to Reveal Energy for this. Appreciate this great presentation. And please join us again this at the end of this month for another presentation. We're looking forward to it. We will be sending out media and such on that. And again, Erica, great talking to you. And we'll keep in touch with you. Thank you very much.
Thank you all.
Thanks.